Hello, my name is Arya Peruma, and welcome to this first machine learning module tutoring session. Today we'll be covering logistic regression with one feature, but more specifically how to implement Keras, which is an open source library that provides our Python interface when looking at artificial neural networks, which we'll be doing later on, and is also a high-level API of TensorFlow, which I'll also be showing everyone in today's session as well. In this session, we're also going to be looking deeper into the Python programming and how we can use logistic regression to actually do this and predict and analyze things from our data. So let's get started. So hopefully everyone can see this code over here. And essentially, I'm in a Google Collaboratory notebook. And the first thing that you need to do is you have to definitely import the libraries and APIs, so like the Keras and our libraries that we learned before, such as Matplotlib, NumPy, Pandas, and Seaborn. And essentially, what I did here is I used Keras, which, as I mentioned earlier, a high-level API of TensorFlow, which is why you see it imported like this. So you see it imported as a branch of TensorFlow. So you have the TensorFlow.keras for the models, and as well as the TensorFlow.keras for the layers. And I've imported the dense activation, which you'll be seeing later on how that comes into play, as well as the sequential models. So after that, of course, as I said before, we also imported our standard libraries, which we talked about before. So these four over here, as well as the SK learn as well. So now that you can see that I've imported everything, let's move on to the next cell. And over here, we have this piece of code over here. And this essentially, we've seen this before. This basically mounts this to Google Drive. Since I am using a Google Collaboratory notebook, this works really nicely with Google Drive. So if I have any data in my Google Drive, I'm able to easily mount it and import it inside here. So basically, I've just mounted that. And for this specific session, I've actually used a data set for tumors, so cancerous tumors. And essentially what I've done here is I've been able to use logistic regression to create predictions and analyze this data, which I'll be showing everyone later on today. And essentially what you can see is that I've mounted that, and essentially that is what will extract the data into my code. So now that we've seen this, I'm just going to quickly show the data that we'll be looking at today. So moving on over here, as you can see, this is the data set that I used in this code. So essentially, as I mentioned previously, this is a data set for the size of the tumor. So we have the features and labels. So remember, the features were the X values while the labels were the Y values. And essentially, we have the features and labels. So feature is size of tumor. And as you can see, there are many different sizes here in the data. And we also have cancer, so 0 and 1 for cancerous and not cancerous. So we have that as our label as well. So now that we've seen our feature and label values, as well as had a good idea of what our data looks like, what we're going to do is we're going to go back over here, and we're going to be able to look at the rest of this code. So essentially, the features and labels, first of all, are instantiated over here. So as you can see, I've been able to say what the X value is and what the Y value is. And essentially, we have the X value, which we saw before was the size of tumor, and the Y value, which we saw before, which was cancer or not cancer, depending on the 0 or 1 value. And essentially, we've just instantiated those. Now going over here, we actually get into the logistic regression portion over here. So what I've done over here is I split this into training and testing sets for both the features and labels. So I've set it into a training set for the X and Y, as well as a testing set for the X and Y individually. And with that, I've been able to actually split those off, so we're able to analyze those better. So when we look at the test size itself, as you can see, the test size is going to be 20%. So we also split the training and testing sets for both X and Y, which are the features and labels as mentioned before, and we also have the random state value to tie that in as well. So now what happens is for the next cell, I've essentially created an object which scales. So after pre-processing this scale, as you can see, we have the pre-processing function set in place. So now that we've actually pre-processed it, we set this to the standard scalar value. So standard scalar, as you can see here. And as you can see, we actually use a specific equation to actually be able to compute this. And we actually compute the mean in the background. And basically what happens is it's going to be running the standard deviation calculation scale, and it's going to be running it. So I'm going to show everyone that equation over here, which I'm going to talk about. So we have, let's add a code block. And essentially this is the equation. So we have z equals x minus u divided by s. So essentially, this equation is used to standardize features by removing the mean and scaling 2-unit variance standard score samples of x, and basically that's calculated with this specific equation. So that's basically what I said before. It computes the mean in the background and also runs this standard deviation calculation to basically run the scalar values. So I'm going to delete this over here. And going back to this one, we basically create an object-like function. So this line over here, we're creating an object-like function, and basically the scalar fit x train. So the x train over here basically uses the info in x train to compute the mean and standard deviation, which is going to be really useful when we kind of graph all of these things later on. So now we actually take that trained set and use the transform function over here to transform the scaled set, the scaled train set, into a test set. So basically we're scaling that and transforming this training set into a testing set for the features. So now that we've looked at this, that's basically kind of the background code, or like the very stable code at the very beginning, which is kind of the standard that we need to be writing first. After that, we actually are now going to be bringing in even more of the logistic regression. So that basically comes over here in this block. So if you look at this, I'm going to be entering this over here. So just looking at the first 2 lines over here, if you can see that we create the model over here. So as you can see, it says model equals sequential, basically creating our model. And as you can see, a lot of the commands that you see here are basically applied in something called neural networks, which we'll be explaining in another tutoring session. And basically, if you can see that I've actually added an activation to this model. So I've said model.add dense. So basically, if you saw over here, I've imported dense and I've imported activation. So that's why I've been adding those 2 over here. So I've added the dense and the activation to this model. And if you remember before, when we did our topic on linear regression, there was no activation added for that. But now we do need to do that for logistic regression. So basically what I've done is I've applied a sigmoid function after the linear transformation takes place. So after this, once we actually create the model, we have to use the compile function in Python. So that's over here. This line over here, we use the compile function in Python, and this essentially consists of us telling our code what the loss function is going to be, as well as what the error is going to be. And in this case, it's going to be a binary cross entropy, which compares each of the predicted probabilities to actual class output, which can be either 0 or 1, as we saw at our labels for our tumor data. So it can be either 0 and 1, as I said before. And if we go back to this data over here, our tumor data, the cancer values for the labels were all put in 0s and 1s to instantiate or denote if there's cancer or no cancer. So going back here, that's basically what the binary cross entropy is for. So now the optimizer, which is over here in this line, over here, the optimizer is going to be of type steepest gradient descent, which we did look at previously when we talked about linear regression. So now that we actually did this, we are ready to train this model, which is the purpose of the model.fit function over here. So the model.fit command will be able to allow us to do that. So what we're going to do is our scaled x value and y training value are actually inputted. And with this, we actually try to find what is to fit in this model. So what we can actually fit into the model as effectively as possible. And the epoch over here, as you can see, it says epoch equals 16,000. So in the epoch, we see how many steps we are going to do of gradient descent, and the verbose is basically providing the additional information of the background actions of our computer's computations. But for this, at this point, it's not really necessary to set a verbose value. So I put that to 0 because we don't really need to see the background calculations at this point. So now what we're going to do is we're just going to next equate all of this to JList. So JList, as we learned before, is the error after each iteration, which we touched upon when we did talk about linear regression. So as you can see, I've ran the error to ensure that we did enough iterations, and if we did this correctly, we should get a graph that looks like this. So I just use plt.plot, and I have plotted the error, which is JList, and that basically uses the matplotlib to plot this graph. And if we actually have done all of these computations correctly, what we should see is we should see a curve of this graph. First of all, we should see a graph, but then we should also see a curve of the graph not going straight down. As you can see, it's a bit better. So it's not going straight down, but it's going kind of at a straight curve at the bottom. So it's not going drastically down. So basically, the curve of this graph tells me that it has settled, and this means that we have done enough iterations. So if you actually try to do this yourself and you see a graph going down more drastically, so the slope is way steeper, you should actually try changing your epoch value and perform more iterations in that way. So the epoch allows us to see how many iterations were performed, and we have performed just enough iterations that our graph ends up looking like this. So now looking at model evaluate and training it. So we have the JTrain and we're training that. Now looking at that, this is going to give me the cross entropy error on the training and testing set. And what I'm going to do is I'm actually going to validate this by printing both sets. And we would generally expect the error to be way larger on the test set because we trained the model on the training set. So the model knows that the training set is trying to fit inside the trained set. And because of that, we know that the error would be larger on the test set. So as you can see, that is correct over here. We do have that conclusion to be correct. And now that we've been able to test that, we can now move on to actually predicting the probabilities of all of these. So now I'm going to talk to everyone about recall, precision, and accuracy. So as you can see, we have all of these factors on the test set, and now down here we have done it on the training set as well. So over here. So when we compare, the precision is definitely higher in the training set. So I've done the precision, recall, and accuracy testing on the test set as well as on the training set. So these two boxes, so this cell and this cell, we have to be able to compare those two. So if you see this, the precision is definitely higher in the training set. So if you look at that over here, precision is 0.94. Over here, it's only 0.64. So we definitely have better precision for the training set. When it comes to the testing set, we have the accuracy higher in that set. So now when we compare those, we're actually able to see that the accuracy is higher in the training set, and the precision is higher in the training set as well. But when we look at that, the recall is definitely much more higher in the testing set. But actually, when we look at this, the recall is not that much higher than that of the training set, but it is higher by a bit. So definitely it is better recall for the testing. So now that we're able to look at this and we're able to compare how the the predictions for the training and testing set compare, we're able to see that the prediction numbers between 0 and 1 are going to be the probabilities. So when we see the position, it's all between 0 and 1. Everything here is between 0 and 1 and 0 are definitely included in that. And this is just simply because the label values were 0 and 1 when we saw it in the initial tumor data set initially. So now, taking the predictions on the training set, since the training set is a bit shorter or they have a bit smaller numbers, I'm just going to be able to print that and show everyone how that looks. So essentially taking the predictions of the training set, we're going to be looking at them. So what are the predictions? So the predictions are actually going to be numbers between 0 and 1, as we saw on the labels of this specific data set, as I said before. So I'm going to be showing the probabilities for the test set over here. So that's over here, as you can see, this array. So after this computes the probabilities, this specific element of the array, it'll be sent to 0 because this is less than y hat. This one is greater, the second value is greater than y hat, so it will be sent to 1 and so on. And as you can see, in the predicted values, we have those exact same things in the array. So y hat, this will be sent to 0, this will be sent to 1, this will be sent to 1 as well since it's greater. This will be sent to 0 since it's less. Then y hat, which is going to be 0.5. And we keep on going. So because of that, we have these final predictions in our array. So going back over here, so that's actually pretty much all for this lesson. Today we learned about logistic regression with Keras and how to use the training and testing sets to compute the probability and predict values more effectively. I hope everyone enjoyed and learned something new, and I hope to see everyone in the next tutoring session. Thank you everyone for listening today, and I hope you all enjoyed.